So the next model, which is the most commonly used model, is the diffusion model. The diffusion model is used to predict pollutant spread in the atmosphere from one source. These models help in understanding the distribution concentration of pollutants over time and distance. So the model assumes pollutant disperse in Gaussian normal distribution pattern downwind from a point source, meaning that if we look at this, let me just put the pointer. If you look at this source over here, this has a stack, and then the pollutant comes out of a stack. So it goes a little bit up when it starts, a little bit vertical above the stack height in a distance of delta H, and then it starts to be distributed in what we call a Gaussian distribution. The Gaussian distribution is the normal distribution that you've learned in statistics before. And let me remind you a little bit of what a Gaussian distribution is. You remember when you had in statistics some independent variable and some frequency and on the y-axis, and then you get some distribution that looked like this. And then you said the normal distribution that actually occurs as a maximum, and everything is around one mean value, and then it starts to faint in both sides, faint down in both sides, and so on and so forth. So this is the normal distribution is a real pattern that describes a lot in our life. For example, if you look at population in Al Ain, you will find that they are normally distributed around some specific age value, and then the more older you go, the less number you have, the younger you go, the less number you have, and so on and so forth. This really happens in nature a lot. So now, basically what we're saying that I'm sorry, go back, that along the distribution axis, when it is distributing in the wind direction, X, so this is X, right? It's a parallel to the value over here. So if you look at this direction, which is the Y direction, you will find that the pollutant at any time is following a normal distribution similar to that one. If you look here, it will be a little bit now narrower distribution. If you look here, it will be a much wider distribution. However, the area under every curve is always the same. So this area, which is the total amount of pollutant, is equal to that area, which is the total amount of pollutant, equal to that area, which is the total amount of pollutant. So this is what is called, or what is meant by normal distribution over its path. Now let's look in the other direction, which is the y-axis. Let me use a different color. So now let's say we are looking at this direction, which is the z direction. So we will find that the pollutant here is distributed in a normal distribution like this one. Here it will be a wider distribution. That's the z. So it will go like this. And here it will be even wider and wider. So it will go like this. Again, this area is equal to that area is equal to that area. So basically what we are saying that while the plume is going away, this is the whole, it's called the plume, right? The whole thing. While the plume is going away from the source, it's getting dispersed in the y direction and getting dispersed in the z direction. So the value in the mean is getting less, in the middle is getting less, and you start to get more values, more and more distances on the edges. So this one becomes this one now. See, this one becomes this one. And then finally it becomes that one. So it keeps flattening in the middle, and it keeps getting wider on the edges until you don't see it because it's a really straight line. That's when it's completely dispersed. And this is a very good approximation that actually means a lot. So if you really didn't understand this, please stop the video right now, go back, listen to it, and try to understand it again, because we will build a lot on this. So I really want you to make sure that you understand this concept. Let's assume that you understood the concept and you don't need now to go back and watch the video again, and we can move ahead. So we will use this equation. Let me just get the pointer back. This equation, C equals to Q over 2 pi sigma y sigma z u e to the power minus y square over 2 sigma y square e to the power negative z minus h square over 2 sigma z square. Now, what are these? C is the concentration of pollutant at any point x, y, z. Remember that this is x direction, this is y direction, this is z direction. So now I can use this equation to tell me what's the concentration here, 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 or even here. Whatever the coordinates y and z, I can use this equation to get the concentration. So this is a very powerful one. Remember, compared to the previous model where the concentration was equal everywhere, this model provides a much improved prediction than the other. Equals to Q. Q is the emission rate of the pollutant. So how much emissions are coming out of this stack? So now let's see that this is the very first assumption that we make, that Q is constant. So we are assuming that the stack has a constant emission rate coming out of the stack over 2 pi sigma y. Now, sigma y and sigma z, they are dispersion coefficients in the y, which is the crosswind direction, and z, the vertical direction. So these are parameters that we use to describe how much flatter is it getting. So basically, this tells you how much or how the shape is changing in the vertical direction and in the crosswind direction, in the y direction and the z direction. Times u, which is the wind speed, as we know earlier, e to the power negative y square, which is the y direction, how the coordinate of the y, over 2 sigma y, so we know that already, e to the power negative z. What is the z? That's the coordinate in the z direction, minus h. H is not the stack height, but it's the effective stack height, which is h is equal to h, small h, which is a stack, plus delta h, which is the rise above the stack, the plume rise, over 2 sigma z square. Now we know the most important equation that we will use in the diffusion mode. So again, what are the limitations here? I want you to think about the limitations of this model, similar to the ones that we talked earlier. Does it assume constant wind speed? Yes. Does it assume constant wind direction? Yes. So it has a lot also of assumptions that, similar to the older model, we had problem with. But I want you to think about what happens in the other model when we had 40% of the time blowing from one direction and 60% of the time following another direction. So we could actually add them up. So do you mean now that we can apply this equation until the wind changes direction or changes speed and then reapply it? Yes, actually, this is how exactly this is done. So let's say it's now exactly 2 p.m. The wind has this direction and has this speed. So I apply, now I know the distribution as of 2 p.m. 2:05, wind changes direction, now new speed. I do recalculation, now I know what is the new concentration. 2:10, 2:15, I keep doing this every 5 minutes, every minute, whatever, however I have data, I recalculate this model, and now I can have new distribution that happens all the time. So there is another assumption that this happens instantaneously, meaning that I can calculate the X, let's say 5 kilometers away here. it takes time for this, with this wind speed, to reach here. However, my assumption is that this distribution happens instantaneously, and this is kind of an acceptable assumption if you are looking on the impact of this model over very, very long periods of time. So basically, we are looking on years, not on minutes. So we keep doing this or running the model for a period of 5 years usually, by changing the wind direction, let's say every hour or every 10 minutes or every 5 minutes. So let's assume you are a person riding along with the air. That's what we call Lagrangian viewpoint. So bird's view, or if you are an air balloon right here, and you are going along the plume, what will happen? Initially, the concentration of the pollutant is 0 upwind of the stack. So in front of you, there is nothing. Next to you, there is everything. As we pass directly over the stack, we encounter a high concentration of pollutant. Now that we are right here, we are coming this direction. Here, there is no concentration. Now we come here, and it's just everything so turbulent, all the concentrations that we see at the time. The high concentration localized in a thin thread of contaminated air directly over the stack. Now, after passing the stack, the thread of contaminated air expands due to turbulent mixing, and the expansion follows a Gaussian distribution pattern in both horizontal and vertical direction. Let's solve a problem. A factory emits 20 grams per second of CO2. Just get the pen. At a height h. The wind is 3 meters per second. At 1 kilometer downwind, the values of sigma y and sigma z are 30 meters and 20 meters respectively. What are the SO2 concentration at the center line of the plume and at a point 60 meters to the side of 20 meters below the center line? So the center line values are those for which y is equal to 0 and z is equal to h. So both terms in exponential are 0, because remember it was z minus h. So z is h, so h minus h is 0. So now we get the exponents are equal to 0, since e to the power 0 is equal to 1. So now this equation, z minus h, this will be 0. So this will be 1, the whole thing here. 0. So this will be 1. Y is also equal to 0. So also this will be 1. So we end up only with this part of the equation. Q equals to Q over 2 pi sigma y sigma z u. So we just substitute Q 2 pi sigma y sigma z. And this gives us the 0.00177 gram per meter cube equals to 1,770 microgram per meter cube. And at this point away from the center line, we must multiply by the expression. So if we want now another point, which is far away, we need to multiply this by e to the negative 1 over half 60 by over 30 squared plus 1 over half minus 20 over 20 squared, and which is equal to 0.0818. So we will multiply the value that we got here times this. This is basically the application of the equation when you put the z, the actual z and actual y that we want. So next video, we will figure out how can we get the values of sigma y and sigma z. Again, remember guys that and girls that sigma y and sigma z here are given, but we really don't know how to estimate them. Thank you for watching.